We saw in the last video that as we increase the number of compounding periods per year, the amount of money that we earn ends up increasing. However, it starts to increase more slowly as the number of compounding periods gets bigger. So it didn't appear like it's going to get bigger and grow indefinitely. It looked like there was going to be some sort of limit. And so what I want to do is I want to look at this limit as n increases indefinitely. So I'm going to take this formula and I'm going to rewrite things a little bit in a way that's going to help us explore what's going on. So we're still going to have p on the outside, but I'm going to use brackets now, and I'm going to rewrite this as 1 plus r over n to the n over r power raised to the rt power. I've basically rewritten nt as n over r times rt. These are equivalent because we can see the r's could cancel out, giving us nt. So now what I'm going to do is I am going to let m, I'm going to throw in a new letter, I'm going to let m be n over r. So wherever we have an n over r, we're going to replace it with m. So on top of the parentheses, we're going to have an m. And since m is n over r, if we have r over n, that's the reciprocal of m, so this is going to be 1 plus 1 over m. And what I want to do is I want to look at what's in these brackets. Now remember, we wanted to see what happened as n got larger and larger. The number of compounding periods in a year getting bigger and bigger, going towards infinity. And if n is getting larger, that means m is also getting larger. So we're looking at what happens as this quantity, 1 plus 1 over m to the m, gets bigger and bigger. But we saw in a previous lesson that if we look at 1 plus 1 over m to the m power, and we look at what happens to this as m gets bigger and bigger, this quantity gets closer and closer to a particular number, and we called that number e. So this quantity is going to be getting closer and closer to p times e to the rt as m approaches infinity, which is what happens when n approaches infinity. So as the number of compounding periods gets bigger and bigger, and instead of compounding monthly, we're compounding daily or hourly or by the minute or even by the second, then as n approaches infinity, as we're getting more and more of these, the formula that we have gets closer and closer to p times e to the rt, and we call this a limit. We call this a limit, and this is something that you're going to see in calculus. We spend quite a bit of time looking at limits, but right now, all we need to focus on is that this is the formula we would have if we were compounding continuously. Instead of every month or every day, if we were compounding every moment as we went forward through time. So let's write this out. Continuously compounded interest is calculated by a of t equals p times e to the rt, where p is still the principal, r is the annual interest rate as a percent, t is the time in years, and e is the number that we defined in a previous lesson. Remember, E is approximately 2.718, etc. So this is a formula that gives us how much money we would have if we were compounding continuously. So let's look at the same problem that we looked at before, where we were investing $1,000 at 12% interest for 3 years. But let's look at what happens if we're compounding continuously instead of compounding annually, semi-annually, monthly, or daily. So here our amount after 3 years is going to be given by the formula P, which is 1,000, times E to the RT. R is 0.12, T is 3. And if we use a calculator to calculate this, we will get an approximation to the nearest cent of $1,433.33. This is not that much more than if we were compounding daily. When we were compounding daily, remember, it was the same dollar amount, but 24 cents instead of 33 cents. So we've made an extra 9 cents by compounding continuously instead of daily. And I don't know if there's any situation where money is compounded continuously like this. But we wanted to see this for 2 reasons. One, there is a limit to the amount of money that we can make if we're increasing the number of compounding periods per year. And 2, we're going to see some other real-world situations where some sort of quantity is modeled off of the natural exponential function. So we're going to see e to a power in other real-world scenarios as we move forward. Therefore, we want to make sure that we're getting comfortable with dealing with e.